Okay, so in the first part of our interference tutorial, I explained you how you you can construct a vector containing an audio file and add that sample by sample to another vector containing another audio file, both these vectors one-dimensional, and you get a sum. If you add them, you get a sum, which is another one-dimensional vector that contains both audio files. As with any sum, it's really hard to determine what the summands are just by the value of the sum. For instance, 10 might be 7 plus 3 or 8 plus 2. It's really hard to determine the two components just without having information about them, just by looking at the sum. But as you saw, when we add these two things up, our ears are able to parse precisely what is a bottle pop sound and what is an alarm sound. That is because the nature of our inner ear works as a filter for frequencies. Later, we're going to develop ways of decomposing sounds. For now, what's most important is to see that there's this linear, and by linear I mean this addition-like relationship to sounds. So they interfere in one another additively. So now for our next installment here, let's fire up. And I'm going to construct two synthetic waves and add them up and start displacing them in phase. At first, very slightly, and then more drastically to understand better the effects of interference. So the first thing we're going to do is determine the sampling frequency or sample rate. Let's take 44100 and the semicolon is that so we don't get an answer from MATLAB. Displayed, okay, and then the period of sampling is going to be 1 over the frequency of sampling. This means that t is the duration in seconds of each sample, okay, 1 over 44100. And very, very short, obviously. And we also need a duration for the whole signal, which I'm going to put 2 seconds. And a time vector that I'm going to denote lowercase t, and this is going to be from 0 to duration d in steps of capital T. Okay, now we're ready to define our first vector. Let's call it x. So s is going to be sine of 2 pi times some frequency of oscillation, let's say 440, and times obviously the time vector. And having this defined, we can certainly plot this thing. Not going to be very instructive because there are way too many samples per second, and we'll see just a very filled up picture. We can certainly zoom it in, and we'll see that we can identify the oscillatory nature of this thing, but since it happens all so fast, plotting is not our friend here. So let's just listen to it out x and at this sampling frequency. Okay, so this is 2 seconds of that 440A here. Okay, so the next thing we're going to do is create another vector, which we're going to denote y. And y is going to have the same frequency as x. However, we're going to obviously, if we add x and y together by the results of the previous video, we're just going to get another signal whose samples are just twice as large as x's or y's. But in this case, we're interested in looking at how this thing works if we just shift the signal y. At first, very slightly. Let's just shift it by pi over 16. And let's see how it goes. Now let's create another vector s, let's say, or z maybe, which is x plus y. And see what z sounds like. Sound z at 44100. Okay, so it's definitely a little louder and a little sharper, if you will. Okay, so what do you think is going to happen if we go all the way and set y to be displaced by pi? Now we can go ahead and update our vector z. What do you think is going to happen? Well, let's first hear this thing. Oh, yeah, that's right. Nothing. They cancel out entirely. So maybe we should go ahead and plot this thing to see what's going on. This is our time vector. This is z. And this is how it looks. Kind of weird, but these are very, very small values. This is 4 times 10 to the minus 13. And these values here are due entirely to machine imprecision. And in actuality, these things canceled out completely. That's why we don't hear anything.